Earlier we talked about how a moving charge creates a magnetic field.
If moving charges have something to do with making a magnetic field and current is just moving charges, then only currents make a magnetic field. And we all have experimented with that, like even if we were even if it was only when you were in elementary school, where you wrapped wire around a nail and hooked it up to a battery, and you're like, oh, I can pick up a paper clip. So that is an electromagnet, and it comes from the fact that moving charges create a magnetic field. What's the value of that magnetic field? Well, it turns out that the value of that magnetic field, the magnitude of a magnetic field is associated with the current in a current carrying wire, is B equals mu0 times I over 2 pi r, where mu0 is this quantity called permittivity of free space. The value of mu0 is equal to 4 pi times 10 to the minus 7 Tesla meters over amps. Okay, so you might wonder, well, why are we have a 2 pi in mu0 in the numerator and we have 2 pi in the denominator? So don't the factors of 2 pi cancel? Yes. But there are other equations that physicists in general use more often than this one. And in those equations, it's convenient to have the 4 pi in the mu0 term. So we just do. I, of course, is the current in the wire, and then R is the distance away from the wire. So if I have a current carrying wire like this, here's I, and if I wanted to find B right here, some distance R away from that wire, that would be R. Well, that equation is for the magnitude. Magnetic field is a vector, so I got to tell you how to find the direction too. The direction, it's another right-hand rule. I know you just love right-hand rules. Okay. The right-hand rule for finding the direction due to the magnetic field from a wire is this. So you grasp the wire, or pretend you're grasping the wire, with your fingers while your thumb points in the direction of the current. And then if you do that, your fingers will be curling in the direction of the field. I am going to do my best to explain it in words, but what if I were to look at it from the point of view of the wire, where I've got wire, the wire is coming at me like this. This is the current now. It's coming out of the screen. So that's current. So in that case, I would point my thumb towards myself. My thumb is coming out of the screen. And now my fingers curl in the direction of the magnetic field everywhere. So the magnetic field, due to this one, looks like that. So see how it's going down on the left and up on the right. It goes in opposite directions on different sides of the wire because it's curling around in a loop. Think of your fingers as a circle around the wire. No, in this example, in the one that I just did, current is coming out of the screen. Well, I'm getting requests to explain number 4 in the homework. In number 4 in the homework, we have a positive charge moving to the right through a magnetic field that is pointing out of the screen or page, whatever. So you point your fingers in the direction that the charge is moving. Then you point your palm in the direction that the magnetic field is facing. So if you're looking at your screen, not at me, but if you're looking at your screen, the magnetic field is pointing out of the screen. So in order to face my palm in the same direction as out of the screen, I got to turn my hand over. Now I've got my fingers pointing in the direction of V, and my palm is pointing in the direction of V, out of the screen. Look at your screen, not at me if you're here. And then my thumb is pointing down, which is the negative y direction, and you'll see that on my copy it tells me that that's what the right answer is.
Let's go back to the equations.
If a magnetic field, or if a wire makes a magnetic field, but in the last lesson, we learned that a magnetic field exerts a force on the wire. Well, if a wire makes a magnetic field and a magnetic field exerts a force on the wire, you can't exert a force on yourself, so the wire won't do that. But if you get two wires close to each other, they will exert forces on one another. We got wire 1 and wire 2. The force on wire 1 due to wire 2 is going to be equal to the magnetic field due to wire 2 times I1, that's the current through wire 1, times L, the length of that wire. So now we're just telling you where the magnetic field comes from. That's the only thing different about that equation than what we did last week, is I'm just telling you that that particular B is coming from a different wire. Okay, but today we learned an expression for that B. So let's substitute in the equation up at the top of the screen for B2. So now I have mu0 I2 over 2 pi r, where r is the distance between the two wires. I still need the I1L. Now I can combine terms, and I have mu0 times I1, I2 over 2 pi L over 2 pi r. And actually our book, so r is the distance away that you are from the second wire, the distance away that you are from the wire that's making the magnetic field. Our book says, well, let's call that the distance between the two wires and rename it D. Doesn't really matter what you call it. But if you want this equation to look exactly like it looks in the book, then we need to write instead mu0 I1 I2 L over 2 pi D, where D is the separation of the two wires. L is the length of the wire. And this is for force, magnetic force of two parallel wires on each other. I plugged this in to find the force of on wire 1 due to wire 2, but remember Newton's third law? So it's the force of wire 2 on wire 1 too. So far I've only been talking about straight wires. I've only been talking about kind of one strand of wire. Well, lots of electrical devices, they have a bunch of wire wrapped around something. You might see a cylinder, a solid cylinder of something, and it's got wires, wrapped around it like that or something, so that it goes around behind the thing like this. So evidently, you see that enough that you think, oh, that must be important. Loops of wire, having a bunch of different loops of wire like that around something, that must be kind of important. Well, having a lot of loops of wire wrapped around something, or even if they're not wrapped around, having just a bunch of coils of wire, circular coils of wire all together like that, that's called a solenoid. Probably heard that word before, even if you don't know what it is. Well, now you know what it is, at least from a physics point of view. So your car, so probably if you've heard this word, it's in the terms of somebody said their solenoid was bad in their car. Well, your car does have a solenoid. That's a bunch of loops of wire wrapped around a solid core. Your car uses that in its starting mechanism, because if you want to start your car, then you have to make some switch close that normally is open, because if the switch was normally open on the circuit that connects your car battery to your starter, then your car would just be continuously trying to start. And you don't want that. You want it to only start when you say it's time. Okay, so you need something to physically connect one part of that circuit to the other. Like you have to basically throw a switch. Well, you don't want to get out there under your hood and physically throw a switch. So what you do is car battery is hooked up to the solenoid, and then when you turn the ignition, that lets current flow through that solenoid, and the force that the solenoid exerts on the wire on the other part of your starter will physically pull one of those pieces to the other and physically make that connection. Then current can start flowing. It uses the fact that wires that are carrying current, they exert a force on one another. Well, if you have a coil that has N loops of wire, so we've got some kind of a coil, and it's got, say, N loops, so N can be 1 to anything, then B is equal to N U0 I over 2R, where R is the radius of the coil. You can also write it in terms of little n, which is the number of turns per unit length, and that's in lab